Hello Math 8 students. This video explains dilations and similarity. Where have you heard the word dilate before? When I hear the word dilate, I think about going to the eye doctor when they put drops in my eyes to dilate my pupils. What happens when they do that? When they dilate your pupils, they're changing the size of your pupils. They're making them bigger so that they can see inside. And that's exactly what a dilation is. A dilation is a non-rigid transformation that changes the size of a figure. Notice that it doesn't change the shape, it only changes the size of a figure. So remembering that at the eye doctor they dilate your pupils is a great way to remember what a geometric dilation is. Let's take a look at a dilation. Remember, it's a non-rigid transformation. The shape of the figure isn't changing, but the size is going to change. Now, we can do this very easily with computer software where we enlarge the figure. This is a dilation. We can also perform a dilation that changes the size of the figure by making it smaller. When we are dilating a figure, there are two things that it requires. The first thing that it requires is a scale factor. Scale factors, we use the variable k. You might remember that we also use the variable k when dealing with proportions, and that is going to come up here again soon. K is the scale factor, and if k is between 0 and 1, k shrinks the figure. It's a dilation, but it shrinks it. And if k is greater than 1, then the figure is enlarged. K greater than 1 will enlarge or expand that figure. The second thing that dilations need is they require a center of dilation. Here you can see my original triangle. You can see that I have enlarged it, and you can see that I have shrunk it. And you can see that I've also drawn a line that goes from each vertex. This vertex to this vertex to this vertex and all the way back. And I repeated that with each one of these figures, seeing that I was able to go all the way back. And interestingly enough, every one of these lines goes back to a single point. That point is the center of dilation. You can also use the center of dilation to help you enlarge or shrink figures. Simply choose your center of dilation, draw a line that goes from the center to the vertex of your original, expand it outwards if you are doing an enlargement, and your point is going to be somewhere on that line. Using that information, can you find the center of dilation for these two figures? Notice I have quadrilateral ANTS and quadrilateral A prime N prime T prime S prime. It appears to be the same shape, but just smaller. So, can you find that center of dilation? Remember, the N and N will be on the same line, so draw a line that connects it, but continue it on. A and A prime will be on the same line, so you'll draw a line, but continue it on. We're looking for the intersection of each one of those lines. T and T prime, draw that line and extend it on backwards. Point to where you think it is on the screen. Did you get it right? Even if you weren't precise, hopefully you were able to envision where those lines would intersect somewhere back here. Remembering that a dilation is a non-rigid transformation, it changes the size of a figure, however, it does preserve angle measure. What I'd like you to observe here is angle C, but I can take angle C and I can line it up very perfectly with angle C of the other figure, the dilated figure. I can repeat angle C lines up perfectly with angle C in the dilated figure. That means I didn't change the measure of the angle at all. We can repeat this with angle A. You can see angle A lines up perfectly, so I'm not changing the angle measure, I'm just changing the side lengths. So side lengths change in a proportional way. Although they are changing proportionally, and they're changing according to that scale factor. If I take x prime and compare it to x, and y prime and compare it to y, I'm going to be getting the same value. That value is going to be k, or the scale factor. Similarly, we can compare these these line segments in a shrink as well, and we will still get the exact same values. X double prime over X is equal to Y double prime divided by Y is equal to Z double prime divided by Z, and all of those are going to equal that scale factor that created that shrink. So when we're dealing with coordinates in a grid on a dilation, they're very easy to find with that in mind. We just need to utilize that scale factor. So here I have triangle STU, and I'm expecting to dilate it about the origin. You can do this in a couple of ways. First thing that you can do, since the origin is the center of the dilation, you can draw lines that go from the origin to each vertex of our figure. But what I like doing even more is listing the coordinates. Find the coordinates of S, T, and U. Looks something like this. S is negative 1 comma 0, T is 1 comma 2, and U is 1 comma negative 2. And since I'm dilating it 2, that means the scale factor is 2, I simply take the X value of the coordinate, multiply it by 2, take the Y value of the coordinate, multiply it by 2, and that gives me my new coordinate for the dilated figure. 1 times 2 is 2, 2 times 2 is 4, so my dilated figure is going to have a point at 2 comma 4. Let's continue this for each point. U, multiply each X and Y coordinate by 2, and I get my new U prime. S, multiply each X and Y value by 2, and I get my new S prime. When we plot each of those points, you can see our new perfectly dilated figure with a dilation that's centered about the origin, and each of the coordinates are twice as far from the origin as they originally were. We can confirm this by drawing lines from each vertex going back to the origin, our center of dilation. You can see that each vertex lines up with one another and lines back up with the origin, the center of dilation. We call this collinear. Points in a dilation from the original figure to the new figure are collinear. That means they lie on the same line. Some other interesting things happen with a dilation. Lines are taken to parallel lines. See that? This line is parallel to this one. You can confirm because they have the same slope. This line, SU, is parallel to S prime U prime. Although one is longer, it has the same slope, so that's how you know that they're parallel. The only time that a line will not go to a parallel line is if it becomes the same exact line because of the center of dilation. And that will happen, but we're not going to be discussing it right now in this video. You will be seeing it in a couple of years. So let's review rigid transformations. We have translation, which is a slide, reflection, which is a flip, and rotation, which is a twist or a turn. The reason it's important to discuss these rigid transformations is because rigid transformations will produce congruent figures. But now we've introduced dilation. Dilations are non-rigid. Although dilations preserve, that means that they keep the shape, including angle measure, they do not preserve the size. So that's why we call dilations a non-rigid transformation. And because they are non-rigid, we have to talk about similarity instead. Two figures are similar if they are the same shape, with all angle measures the same and all side lengths proportional. And that's exactly what we saw in a dilation. So another definition of similarity is very similar to what we saw with the congruent definition. Similarity states that two figures are similar if one can be obtained from the other through a series of translations, reflections, rotations, and dilations. So the only difference between similar and congruent is that similar means that they are different sizes, and we got those different sizes through a dilation. So here we can see that example. Here is the original figure, here is the new figure, and I can obtain this figure, I can obtain this figure by simply shrinking, translating, and rotating. It looks like I need to shrink it a little bit more. And rotate it a little bit less. So you can see that these are figures that are similar because I can go through a series of translations, reflections, and rotations, and then they end up being the same figure. That's it for similarity and dilations. I hope that you were able to learn something new. We'll see you next time.